Okay, and welcome back to the programming bootcamp. Um, my name is Gabor Sabo, and hello, Nora.
Hi.
In this video, we are going to talk about Numpy. So let me share the screen and show you this. So Numpy is the library in Python that allows us to use vectors and two-dimensional and more-dimensional matrices and do computations on them. Okay, so it's that's how the definition is. It's the high-level mathematical functions to operate on large multi-dimensional arrays and matrices. Okay, it's the thing is there. It's called ND array. So one has to install it, of course, in pip install numpy. If it's not installed yet, I think Anaconda comes with it, but in any case, that's how you can install it. And then we can start looking at various simple examples here. And later we get to a slightly more complex one. So from numpy, the way most people use it, that they say import numpy as np. So basically, they give it a nickname NP because they are too lazy to type numpy every time. Okay, and it's recommended to you do this because basically every example I encountered on the internet, they use this naming convention. So if you also use this, then you can copy paste from various places because NP is going to be the name of numpy. So now we have NP, and then from NP we can say dot array. We give it a list, a regular Python list, okay? And what it gives us back is what they call an array, a NumPy array, or a one-dimensional, right? It's a vector array of the values 3, 4, and then 7. So in some other programming languages, they have in the language they have a data structure called array, but in Python the same thing is called list. So just to connect this thing, so that's why it's called an array, because that's how it's called in most other programming languages as well. So an array, and this A now represents the 3, 4, 7. I can print it out, nothing really interesting there, but then I can do all kind of mathematical operations on it directly. I don't have to loop over the elements. I just say A times 3, and I get back it multiplies each number on its own, okay? Unlike lists, right, which would multiply the series. Okay, I can say plus, and now it works adds 4 to each element of the original. It just this doesn't change the actual array, okay? So this just returns a new array basically with the new values, but doesn't change A. So here again, I use the same A, 3, 4, 7, and I add them 4. Okay, then I also can get some metadata from it. Dtype is the type of the data, and it says int64. So this means that each value is an integer, so that says int, and 64 means the number of bits that it's using. Okay? It's a little bit wasteful because 64-bit can use a lot of bigger data, and we'll see how we can save some memory if you know that the data contains only small numbers. Ndim is the number of dimensions, so it's one-dimensional because it's just a vector, and the shape of it is 3, and it has to be a comma because it's a tuple, and the tuples, if there is only a single value, it needs a comma at the end. Okay, it's just some syntax issue. Okay, this time I created another one. Okay, it's just another vector, same length. But this time, because one of the elements is a floating point number, if I check the type, it says it's float 64-bit. So it's using each value is now a floating point 64-bit thing. And the shape is the same and so on. And I can also create an array from strings. Okay, and then I get back some object which has a dtype of, and this time is less than U5. And if I understand it correctly, this means that it's Unicode characters and they are 5 characters or less. So I guess it just takes the longest one and then makes each location the same length actually. Okay, the idea here, one of the ideas here is that because these data structures, every data is the same length, when you do the computation, or actually when Python does the computation behind the scenes, it knows exactly where in the memory each piece of data. As opposed to a regular list of Python, where you don't know, each value can be a long one or a short one, so you don't know where is the third one in the actual memory of the computer. And that can mean that actually the operations of Numpy, as I think they can be about 100 times faster than regular Python. So for these specific operations that it's good for, it's really good for. Okay, some links to the basic types and the dtypes. Actually, let me check it out. So this is the explanation. Do I have the list here? No. No, we don't have the list here. But there's all the explanation about NumPy. Okay, so let's create a two-dimensional array. And what we do here is just create in Python, regular Python lists, a list of lists, list of two lists. So this is a list. Sorry, this is a list. This is another list, and then this wraps around the two. So for the outer list, the two elements are two lists. And regular Python would be able to handle if the lists were different lengths, but NumPy needs that they are both the same length. But with the same NP array, I created an object that now represents this two-dimensional array or matrix, whatever you would like to call it. Okay, and then you can print it out. Okay, and you can ask the shape, which is now 2 on 5, 2 rows and 5. You can ask the dimension, which is 2, okay, 2 directions. And here too, you can use the same operations. You can multiply, and this multiplies the individual elements or adds something to the individual elements. So far, the dtype was created automatically based on the values. But if you know that, for example, all your numbers are going to be really, really small integers, so integers that are between 0 and 255, then you know that only the 8-bit is enough for you. So then you can you can say that, okay, in this array, you store each one of them in a type which is called int8. Okay, this means that instead of 64-bit, each one uses 8-bit, so you can use 8 times more data in the memory. And then the whole thing is, the rest is the same. It's just that you explicitly said that what is the type of the data. So this means that you don't have to think about it because you get the default. But if you think about it, that can help you save memory and provide you more location. So here I have the same idea, but now we are generating automatically arrays. One of them is with NP, it has ones. Okay, so it will create a matrix that only has ones in it. Okay, and I said it 4. So it means it's a 4 lengths one. It has only one dimension. Okay. If I want, and I said also that the type of each value is the 32-bit, integer 32-bit. Okay. And the sizes can be 8, 16, 32, and 64, I think. These are the valid types. But somewhere it's listed that what are the exact valid types. Same way you can create zeros. So it's often that you need a matrix that's just ones or just zeros. These can be useful in computations. And here just another example is ones, where I put in a list of 2 numbers, and which meaning the dimensions. Okay, so if it's one dimensional, that's just the number. If it's more than one dimensions, then you give it the list of the sizes in different directions. Okay, and by default, it created a floating point 64. Okay, there is another method called I that can create a matrix with just ones here. And diagonal, I think, is that. Okay. Right. Sorry. Yeah, no, I don't have anything else. You can also create a random data. Okay, so I don't know when is it useful, but maybe for demo purposes, that can be definitely useful. So just random, and it will generate numbers in the range of 0 till 1. Now, this is just mathematical. This is a mathematical symbol, so nothing to do with Python. So the 0 is included and the 1.0 is excluded.
Can you actually change that and set what range you want the random number to come from?
Yeah, I'm sure. I don't know.
Okay.
Yeah. But I mean, if not, then just multiply it with something, and then you have that range. So the result, just multiply it, and then that's the range. And you can also use various random generators. So, and I haven't read all the details about this, but one of them is called that. So apparently this is not the default, but it's called default. I got messed up there. The main point here is that you are various ways to generate these random numbers, and then you can read about it and find out whatever you like. Okay. You can also get random integers if you call the randint. And these two also has its own random generator, which way to generate the random numbers. And here we say, yeah, so I think this is slightly different. So here you say, what is so the numbers will be between 0 and 10. And this is the size of the actual matrix that you get. Right. Here we are going to divide the elements. So we have the array. If when we divide of integers, right, you can see these are integers, and then we divide each value by 2, and the result is going to be an array, but with floating points already, because they had to become floating point. Okay. You can have other methods on the matrix, for example, transpose. So we have the array, and then you can transpose, and then we get it in the transpose way. So I guess there are tons of other operations there. Okay. What you have to remember, though, is that this transposition. So what was this? I had A, then I called A transpose, and I got B, and I assigned it to B. But if I look at this, if now here I change one of the values in A, then it changes in both B and A. So this is just this references still to the same data structure, same place in the memory. So it's a reference and not a copy.
So it's like the shallow copy was before?
No, not even shallow, without any copy.
Okay, just a reference.
Just nothing, yeah. So just like an assignment was in lists.
Right.
So if you'd like to copy it, then you can copy the call the copy method. And so this key creates a copy of it, and then you transpose it, and then we got back the transpose version. And now if I change one of them, it doesn't change the other one. The default is to save memory, right? Okay, so these were the I mean, I don't know, some of the operations. You can also take two matrices and add them together, two matrices, and then they will do it element wise. So A plus B, it adds the first element, the same location. I mean, obviously for these operations, the dimension of the matrices has to be the same. And you can also multiply them. Okay, and then they multiply element wise. And then, but there are actually, no, I can't hear you.
Sorry, so does it raise an exception if the two matrices are not the same size or not the same dimension?
I guess so. I haven't tried it, but I guess so.
Right.
Okay. So, but this is just one of the ways to multiply matrices. There are actually apparently 3 different ways. Okay. So I think multiply was the one, and these 3 has methods for it. Okay. So I can say np.multiply and give it to matrix. And then they are the different behavior. So I think the simple one which is called multiply is the one that we saw. That is the same that when you just use the star, the multiplication operator. And then you can multiply matrices by the rows with the columns, right? And I don't know what is the 4th one. Okay, so do we have the output here? No. So let's take this one is numpy multiply vectors. So it says numpy and then Python multiply.
You went into numbers,
Sorry.
not numpy.
Yep. Okay, what do we see here? Ah, sorry, I actually have the results here. I didn't have to do that. So the first the multiply is multiplies by numbers, and then these 2, and I don't know exactly the difference. There's some difference between the 2. Okay, but apparently in this case of, I guess in the case of vectors, they are the same. Okay. I remember knowing all this stuff back in high school. Okay, but I don't remember what I remembered. And this is not something that I do normally, programming part. So I'm showing you parts of it, and then you go ahead and figure out all the rest, which is basically with all the rest happen the same. Okay, so here, yeah, okay, so just more examples, but this time with a matrix. So it's a two-dimensional one, and this is a vector. And how can you multiply them? Okay, so at the end you go ahead and play with this, and that's how you figure out which one of them works. And you can also do them if they are both two-dimensional. Okay, so it's just the examples how they get there. Okay, so what happens? So this can, I don't know how common this can be, but if you read some data from a file, then you might get strings, right? Even though those are numbers, but they're formatted as strings. So here we have an array with all of the elements are strings, but you would like to use them as numbers. So I mean, you can't add 1 to this because they are strings, but you can say astype and then say np.int. Okay, and then this will convert all the values to integer. And then it doesn't change A, of course. It just gives you a new matrix where all the values are converted to integers. And then on that, you can also do operation. Okay. Okay, so let's see how to access parts of the arrays. So we actually saw that you can access elements, and we changed that. It's quite similar to how you do it in these lists. So this is if you have a vector, so it's a one-dimensional array. That's sort of easy. That's how you get one element, and that's how you get a range of the elements, or a slice of it, or a part of the vector. Okay, so element 2 till 5 is so 0, 1, 2, 3, and 4, because the upper part is not included here either. Remember, this slice is also just a reference to the actual underlying array somewhere. So if I got this slice and then I change the value somewhere, then it changes also the slice. And you can copy. Okay, so this is actually, this example is here because in one of the classes, someone asked me how to do this, how to convert each value to ups. And first I didn't know. So I showed him a way to create it yourself. And in a couple of files, I'm going to show how, if there was no apps, how would you able to implement the apps method that will work on the matrix as one function, okay? Instead of going all the elements and doing it yourself, right? So you have a matrix, or just let's say an array, a Numpy array, and you would like to do some operation on each value. One way to do this is just to go over with a loop and do the operation on each one of them. But it's going to be slow, and it's not the way Numpy works. So Numpy allows us to take functions that work on an individual value and make them and vectorize them. So it will work at once on all of the elements, okay? And this is what I did, and this is I'm going to show later on. But here, then, once we did this, and later on we searched for the internet if there is a solution, and actually we found out that there is already a built-in function for it. And the reason I'm telling it this way is because to remind you that basically everything is implemented in Numpy. I mean, not everything, but a lot of things that you would need. So just search for it, and you will find probably the right method. Okay, so here we have a matrix, and then called np.absolute on the and gave it the matrix, the vector. Let's call it array, the array, okay, the Numpy array, and got back another array that was just the absolute values. Okay, so, and this is a single function call, and I don't know how Numpy works behind the scenes, but it's way faster than going over with a loop yourself. Okay. The other thing is if we can do logical NOT on a Numpy array. So I have an array that we haven't seen earlier that each value is a Boolean true or false. Okay, and I can call logical NOT, and then the result is going to be the opposite. And if I have a vector, an array that has some Booleans and some numbers, okay, so this is, then the Booleans are converted to ones and zeros automatically. Okay, I don't know, that's the numerical representation of true or false. But if you call them logical NOT on something that has numbers in it, then it will take these can be taken as true, 1 and 1 is true, so the logical NOT is false, 42 is true, the logical NOT is false, and the zeros become trues. No? Okay. Is it okay? Good. Okay, so this is the example that I mentioned, that we can vectorize a function. So what do we have here? We have the function Fibonacci, or beloved function, right? Which is not, this case is not a recursive version, but what it does is gets an n and then returns the current version of the Fibonacci, or the specific version of the Fibonacci number, okay? So this is just any function that we have wrote in Python that gets one value, returns one value. And then I can call np.vectorize Fibo. And what I get back is a new function. So the input is a function, the output is another function. Okay, it's changed, it vectorized the function. And now I can call vfibo and give it an array, and it works sort of in parallel on all the elements. And it gives you back a matrix that with all the results. Okay. Fibonacci is not a good example because you have all this, you calculate the whole thing again and again. So maybe it's not a good, maybe it should be a lookup like Fibonacci, but so this was, if this is the original matrix, then this is the result, just the series numbers in a result. And you can do it with anything. So which means that now you can have any calculation that you would like to do on an individual element. You don't have to think about the fact that it's a multi-dimensional matrix that you're going to work on. You just concentrate on one single element, write a function, test your function, then you vectorize it and call it on the whole thing. You can also vectorize a built-in function. Okay, so len would work on a string, for example, right? So vectorize it, I called it vlen, and then I call vlen animals, and it gives me the length of each word. Okay. And we saw lambda, right, which is just basically creating a function on the fly, because, well, in the previous example, we created the Fibo function, okay, separately, and it called it. In this case, we have a much shorter function, okay, a function that gets a value and returns true if the length of that value is more than 5. Okay, so these are going to be the long animals, okay, or the animals with the long names. And so we have the animals, just an array, and then NP vectorize this function that we created on the fly. So we don't have a name for this function, but now we have a name for the vectorized version of the function. And then we can call that vectorized function on the animals and get back a list of booleans, because this returns true or false. Okay, so this returns true if the length is more than 5 and false if it's not. So this is the original list, the original array, and this is the new one, which is just booleans. Okay, so apparently the elephant and the praying mantis are long ones. Okay, the snake isn't that long. Okay, so now we have a vector, or we have an array, and we would like to filter out the long ones. So just work on the long ones. I mean, you can use it this way, any filter, but we already have this function. So we create the vectorize the function of the condition, just as we did earlier. Using that, we create the booleans that we saw earlier. Okay, so this is the booleans. And then we say animals and square bracket and put in the vector of the booleans. So this is going to be like, it says that in the square bracket has trues and falses. And this will return us a new vector that contains the values from the original value, every place where this one was true. So basically we got back the long ones. This can be very useful when you have a lot of data and you would like to filter out some data. Okay, size, length, whatever. And this works this way if it's a one-dimensional. What if it's a matrix? What if it's 2 dimensionals? So here I have just an array, okay, just with numbers, scores, whatever. And then I could use this condition. So I don't even need a separate vectorized function now. This condition, and I put it in parentheses just to be clear that that's the operation, and then the result of that is assigned to the other side. Otherwise, I don't think that you actually need that parentheses. Okay. So here we get back something that looks like this. Okay, a matrix of true and false values. And then I can use underscores, so on this one, this matrix of trues and false, and get back a one-dimensional one, because otherwise it would be just values all over in various places, right? So you can't get back the matrix format. Would I get back a vector, so a one-dimensional series of data, of all the data that was true. So in this case, the bigger than 20 numbers. Okay. In this case, we have some names. And it has a brilliant function called has AR in it, which will return true if the text has AR in it. Okay. Any condition here. Okay. So I just came up with this brilliant idea of checking if the name has AR in it. So Mary has, Bar has, Joe doesn't, Jane doesn't. And then I took that and vectorized it. And sorry, I can call, vectorize it and then call the vectorized function on the original matrix, on the original vector. So this I got back the Boolean values. Okay, so these are the Boolean values, these ones. And then I use that on the matrix. So it's sort of combining the two. I'm creating a filtering from a vector and using it on the matrix. And what I get back is, why do I have it twice? I don't know. I get back the, I don't know why do I have it twice. Okay, I just bug in printing. Filter matrix. Okay. Apparently I saved it incorrectly. Okay, so now I get back a matrix of those rows. Okay, in this case, those rows where we had AR in the name. Okay, so here the first two rows, 23 and 9 and sorry, 23 and 10. It's really bad. The output is really incorrect. Okay, so this is 23 and 10. Okay, sorry, 23 and 10. These two rows. Okay, I don't know where did I see 19 here. Okay, these two rows are filtered out because they don't have AR in them. So that's again some combination of filtering data. You can also get all kinds of statistics from the Numpy. So you have this array, and then you can say what is the sum of all the numbers, what is the mean of all the numbers, the standard deviation, the variance, basic statistical numbers. Okay, mean, max, cumulative sum. Okay, so and then and that might be also more a little bit interesting, that there is what we call serialization. Have you talked about serialization earlier?
I don't think so.
No. Okay. So serialization, right. So in a file, what you can save is just a series of characters, so a series of bytes. You can't save a list in there, like a Python list or a NumPy matrix, because that's just the data that's in a rectangle, right? Some data. And what you can save or you can say a dictionary. Think about a dictionary. It's just data all kind of places. You can't save that in a file. You just can save a series of things. So serialization is taking some kind of a data structure and converting it into a series of characters. And then deserialization is taking that string and converting back to the original data. Okay, because a serialization alone wouldn't be that helpful. Okay, so what we do here, and this idea of serialization exists in just Python as well, but here specifically to NumPy, I have an array here, and I can call np.save give a name of a file and the data structure, and it saves this data structure in the file. And then in some other program or in the same program later on, I can load the data structure into memory. So this can be very useful because you have one program that works on some data structure. At the end, you get some result, but it's still the data structure, and you would like to pass it on to some next running, to the following processing. Okay, so that's the serialization inside NumPy with the same and the load functions. And then you also talk with people who use Matlab. And NumPy provides a way to read, not actually, it's not NumPy, but the ecosystem, this Python ecosystem provides a way to read Matlab files as well. So you need to use import scipy.io, and then you can say scipy.io.loadmat and give it the name of the file that you got from Matlab. So it's a data file from Matlab. And in a data file with Matlab, basically you have multiple, you can have multiple of these arrays. So this is the same like an array, an NumPy array, but you can have multiple ones in a Matlab file, and each one has a name. So basically think about it, that's at the dictionary where you have a key and the value is a NumPy array. So when you read it, you got back this data structure, which is a dictionary, and then you can get access one of them. Let's say it was called data. If someone wasn't very creative on how to call it. And what you get back is some variable name. And if you check the type of it, it says NumPy and the array. So it's a NumPy array, even though it's a Matlab file. Okay. So if some other people, that's like a common question. Okay, but the other people in the lab use Matlab. So how can I interact with them? No problem. You can read their data. And if you would like to pass them data back, then no problem either. scipy.io save mat. You give it the name of a file, and then you give it this dictionary where you have some name and your array, and then it saves it. And I think, and you can have multiple of these key value pairs. Okay, so now you can communicate with NumPy people. Okay, you can also stack vectors horizontally or vertically. So here I have 3 vectors, and I call hstack on A and B. And what I get back is this. So I put one after the other. And if I call hstack now on D and C, then it adds the C1 at the end. So it's putting them together because the plus operator, as we used for lists, now does something else. So we needed this other operator. So this is hstack because it's horizontal stack. And same vectors, but this time I'm calling vstack. So vstack puts one on the top of the other. And then I can call again, and then it adds another one. So you can combine, again, I mean, they have to be the same length because, yeah, what did I want to show you here? I don't think that that's everything interesting. uint. Uint is unsigned integer. Okay, so this is A, okay, which is an array, and it has a single value, 127 in it. Now I take and add 1 to this number. So it's 128, okay? And if I remove 1, then it's 127. So far looks good. Okay, so let's put 255 in it. What is in there? 255. So far good. Now I add 1 more. What do I have? 0. Okay, because it's an unsigned integer, so it's basically from 0 till 255. And if you add one more, then it just empties the whole thing. So you have to be careful with this, of course. The int is what we call signed integer. That goes from actually from minus 128 till plus 127. Is this also a range of 256, but it has the minus part and the plus part. And sometimes that's what you need. Okay. And here too, you can see that if I have 127 and I add 1, then I get minus 128. Yeah, it's funny now, but
Interesting logic.
It's I mean, just think about it. I mean, that's the representation. I mean, you have eight bits, now this the previous one is easier. You have 8 bits, eight of them are ones. If I add one, then the representation should be 8 zeros and the new 1. But because I don't have place for that, that's just thrown away. Okay, and this is called overflow. What we call like variable overflow, whatever. Okay, so if you remember the Stack Overflow, the website is quite similar, not exactly this, but that's also, there is something called a stack. Well, you know what a stack is, right? That we can push and pop. So, and it has in some places it has a fixed size, and if you put some more in, then you get Stack Overflow there. Okay, which is a horrible, very low level but very horrible bug. But now, because of Numpy, you can enjoy it, having these bugs. Okay, so that's it. Next chapter is going to be pandas. Any question with Numpy that you could think that?
For now, no.
Okay, so just start one. I don't have any exercises here specifically. Just start using it, start playing with it. And remember, I think I showed you about 1% of it, or maybe less. And just to put you in the correct, I don't know what you think about it. Okay, so you know that you have lots of other things here to learn. Okay, so thank you very much for watching. And if you have questions, I'll try to answer, and then maybe you can add more slides and have some more explanations here. So thank you very much. Bye-bye.
See you.